5th, 2018 edition of Fire on the Fives, brought to you by the National Weather Service Fire Weather Program. Fire on the Fives is a webinar series that presents the latest science and best practices regarding the fire environment and fire weather. Please ensure that you mute your phone or use the audio pin provided. Do not put your phone on hold. You must use the audio pin provided by GoToWebinar if you wish to be unmuted during the question and answer session to ask your question directly to the presenter. If you are unable to use the pin, you may post your question in the question box in your GoTo control panel, and the moderator will ask the question for you. Today's presenters are Dr. Joseph J. Charney, Research Meteorologist for the U.S. Forest Service at the Northern Research Station in Lansing, Michigan. And also Dr. Brian Potter, Research Meteorologist for the U.S. Forest Service with the Pacific Wildland Fire Sciences Laboratory in Seattle, Washington. Jay has been working with his colleagues, Alan Schrock, Brian Potter, and Scott Goodrick to develop a new fire weather index that is focused on helping fire weather forecasters predict and communicate the weather portion of the fire triangle. Welcome, gentlemen.
Thank you very much. All right, so my name is Jay Charney. I will be the primary presenter today, I suppose, and I also want to acknowledge my colleagues. As Larry just said, Alan Schrock, Brian Potter, and Scott Goodrick have been working with me for a number of years now on this effort, and also wanted to acknowledge Jessica McDonald, who has been extremely instrumental in putting together some of the web products that we're going to be showing you later on, and also in helping us get one of the hot, dry, and windy papers published. So with that as introduction, today we're going to be talking about the hot, dry, and windy index. Now, the problem with forecasting wildland fire is that it's very difficult, and as I will demonstrate later in some context, it can be painful. Predicting wildland fire is dependent on processes that span a wide range of scales. Now, most of the existing fire weather forecast tools are either pretty outdated, or at least have been around for a long time and have not been updated, or are known to have flaws. And this naturally leads to the operational community, both the meteorologists and the fire community, to be wary of these tools. So we're asking ourselves and asserting that we can do better than what is out there right now, and we want to try to show that. So to start off, the serendipity, if you will, what sequence of events led to all of this, all of what you're going to see today? How does science happen? All right. First off, scientists go to conferences all the time and sit around and talk and say, okay, what can we do? Let's get some researchers together. What are the big problems and what are we doing to address them? What's been done before and what are we planning to do next? Frequently, these sorts of conversations happen over food and a variety of beverages, and if we're lucky, science happens. So stand back, we're going to try some science. And this is exactly what happened at a Fire Behavior and Fuels conference in Raleigh, North Carolina a number of years ago, when Brian Potter, myself, Scott Goodrick, and Alan Schrock sat around a table and said, what can we do about fire weather indices and fire weather prediction? So we said, okay, let's go back to the basics. Starting point, fire prediction. We all know that there are three components to fire prediction. There's topography, fuels, and weather. But we can assert that not all of the sides are created equal. Now, to demonstrate this is what I meant by pain. I'm going to be using Ali Brash's from Hyperbole and a Half, the better pain scale that she put together a number of years ago that has been gaining a lot of traction in many different disciplines, and we're going to try to use it with respect to fire. So let's start off. For fire prediction, the first thing we need to know about is topography. Now, predicting topography is arguably not terribly difficult. It doesn't change a whole lot, and we have maps. So we can say that predicting or assessing topography is not necessarily the thing that keeps us up at night. Now, the next point, predicting the weather. Now, we're meteorologists. We know that the weather can be predicted, but we also know that it's fraught with peril and there's all kinds of uncertainties. So this gets us up to, say, a 5 on the pain scale. Why is this happening to us? Why do we have to deal with this? All right. Now, the next component are fuels. We put this at a 6 on the pain scale, saying my pain is super legit right now. Ask a meteorologist what's going to happen with the fuels, and most of us are going to say the fuels are changing. But we're not necessarily good at predicting those. That's not our focus. But you put all of them together, topography, fuels, and weather, you get way up on the pain scale to, I am actively being mauled by a bear. This really, really hurts. This is what we mean by difficult and painful. Okay, so we said, okay, how can we make this better? What can we do to help improve this, from thinking as meteorologists sitting around the table saying, what can we do to improve fire weather forecasting? All right, so the first thing is, okay, let's see if we can figure out how to strip away the other issues and focus only on the weather that we have some confidence that we can predict. All right, pain level goes down. We're down to level 4. Okay, we know that there's uncertainty, but we're feeling a little better about things now. All right, so start with the physical principles of how the weather affects a fire. When weather worsens primarily through hotter, drier, and windier conditions, the so-called hot, dry, windy paradigm, or even intuition within the fire community. So we asked ourselves, where do these conditions occur in such a way that they can affect a fire? How do these affect the fire environment? So again, speaking as meteorologists, we think we're looking at bigger than an air parcel and smaller than an air mass. We're not going to suggest that a great big high pressure system is having a direct effect on how a fire is evolving. And we're also not going to go down to tiny little air parcels and microscale stuff, because that is not predictable. And we don't want to try to argue that that's predictable. We also have some sense that surface conditions and conditions in a layer near the surface are both important. So just looking at the surface, we're likely going to be missing things. So we take those ideas and say, okay, how can we take weather information and make them useful? And that leads to the term that we've started to use to refer to indexification. How do you define and test a new index? Now, many of the indices that we use in meteorology were defined over the years and just started being used because they seemed like a good idea at the time. And some of them have been tested, some of them haven't. But the degree to which most indices have been tested is actually pretty sparse. So we decided to identify a number of bullet items or characteristics of the index that we want to establish, or that we want to employ when defining hot, dry, and windy. First, as much as possible, we want it to be easy to understand. If it works, we want to have a pretty good idea of why it worked. If it doesn't work, we want to be able to look at it and say, we can figure out why it didn't work. We want to understand both the success and the failure modes. In order to make this easier, we want the index to be as much as possible continuous, so it doesn't have breakpoints or discontinuities or big jumps in numbers for no physical reason. And we'd also prefer that it not have negative numbers in it. We don't like the idea of an index that changes from +5 to -5 without that meaning something fairly significant. And we also, as much as possible, want to make sure that it can be calculated anywhere, meaning anywhere on the globe at any location on Earth where a fire might happen. All right, so with these basic concepts, we said, okay, let's form a new index. And we didn't originally call it hot, dry, and windy. We considered a whole bunch of different acronyms. But we thought, you know what, HDW works. It's something that parses, people understand it. So we're going to call it the hot, dry, windy index, and we're going to consider the meteorological variables that correspond to hot, dry, and windy, being temperature, moisture, and wind speed. All right, and we're also going to focus on conditions in a layer tied directly to the surface, about 500 meters deep. Now, we chose 500 meters. There are many situations in which a deeper layer could affect a fire, and even when a shallower layer might affect a fire. But we figured 500 meters is probably a pretty good compromise where we could have one number, one formulation that is potentially applicable just about anywhere in the world. And it's certainly feasible to test other numbers, but the idea was it's going to be relatively rare to have a fire of any substantial size where at least the lowest 500 meters is not, doesn't have the potential to affect how that fire is going to behave. We also want, as a basic concept, we want to provide a daily assessment of whether the fire will be difficult to manage based purely on meteorological conditions. Basically, we want to strip away the fuels, we want to strip away the topography. We're going to say, hey, we're meteorologists, we can assess the weather. We're going to leave these other assessments to people on the ground who might be standing in the topography, who can look at it and are staring at the fuels or have other fuel metrics that they can apply to the problem. But we want to consider those to be more local issues. Our concern is what predictable weather can we assess to try to better understand how a fire might evolve. All right, so this led to key realization number 2. Temperature and moisture cannot be considered independently. What we're talking about here with temperature and moisture, generally speaking, is the potential for the atmosphere to dry out the fuels or even moisten the fuels if you want to think in the other direction, but the evaporative potential. How is the atmosphere going to affect how dry the fuels are and how readily they're going to burn? Now, traditional metric, or the most common metric used historically for assessing the effect of temperature and moisture in the atmosphere, is relative humidity. But we argue here that relative humidity is not the best metric for looking at how the atmosphere is going to affect fuels. We're going to argue that the vapor pressure deficit it fits better because it's a difference rather than a ratio. And as a demonstration of this, this is a plot showing vapor pressure versus temperature. So if you look on the x-axis, you see the temperature of 10 degrees centigrade and 35 degrees centigrade. For the same relative humidity, you have very, very different vapor pressures. Sometimes you can have a factor difference. In this particular example, it's probably 6 or 7 times as large. And it is this difference that affects the rate at which moisture evaporates from fuels. So we're arguing that the vapor pressure deficit is the better number for giving a always increasing or continuous example or continuous understanding of how the atmosphere and how the moisture and temperature conditions could affect a fire, the fuels, and therefore affect a fire. So taking these simple concepts, we're going to define hot, dry, and windy as just simply multiplying the U, the wind, U, by the vapor pressure deficit to indicate hot and dry. And we're going to take this a little step further and complicate things ever so slightly by saying we're going to multiply the maximum wind speed by the maximum vapor pressure deficit that we can find in the lowest 500 meters above ground level for any given fire over the course of the day. And so the idea is that this is the maximum potential dryness, hot, dry, and windy conditions that can occur over a burn period for a given location. So, taking a step back, the question is, does hot, dry, and windy meet our three criteria? Is it easy to understand? We hope so. Hot, dry, and windy are pretty simple concepts, and the calculation is also simple. We're just multiplying 2 numbers by each other. Once you calculate the vapor pressure deficit, the rest is straightforward. Is it continuous and not negative? Yes. Both of these numbers cannot go below 0. So if we have a 0 wind and saturated conditions or saturated conditions, we'll have 0, and then it increases as both of those get larger. And can it be calculated anywhere? Yes, it can be calculated anywhere for which we have model data. A little tougher with observations unless you happen to have sounding or some sort of way of diagnosing the lowest 500 meters of the atmosphere, but generally speaking, there's model data available anywhere in the world, so we can calculate it. So now our pain level, we hope, is getting a little bit lower. It's like, okay, we're getting a better idea of how to address this problem. So we have this idea. We put together hot, dry, and windy. We say this is how we expect it to work. This is the theory, but we want to test it. Obviously, we're scientists. That's what we do. So what we did was we used the climate forecast system reanalysis, a reanalysis tool that has global data for going back to 1981 on a half-degree horizontal grid spacing. We calculate HDW on all of these points, and then we can calculate HDW at any point in the world. And for comparison purposes, we're looking at the Haynes index here. And it is, one could argue that the Haynes index is the only other index out there that is weather only, that is often used as what kind of day is it going to be? Is this going to be a Haynes 5-day, a Haynes 4-day, a Haynes 6-day? What kind of day is it going to be? Rightly or wrongly, that is often the way that the Haynes index is applied. So we're going to compare hot, dry, and windy to it just to have something to look at. So the first fire that we're going to look at today is the Pagami Creek fire from 2011. And here's a spread map for the fire. What I want to draw your attention to is that there was one day on the fire where the vast majority of the spread happened. That was on the 12th of September, 2011, shown by the orange on this map. So the question is, if we take hot, dry, and windy, or if we take data from the CFSR for a time series of days leading up to the 12th and after the 12th, can hot, dry, and windy pick out that day? And what we find is, yes, that day does in fact stand out as being quite a bit higher value than the rest of that time period. Now, the other thing that we should point out is that there were other days on the Pagami Creek fire when there was active fire behavior and rapid fire spread, but this day stood out by far as being the most that by being the day with the most active fire behavior, and hot, dry, and windy picks it out and sort of highlights that day. Now, the numbers on the side, we'll talk about those in a little bit. Right now, we don't necessarily know, or that this graph doesn't establish, what does 450 actually mean compared to, say, 200 or 100? What should values should we be paying attention to and which shouldn't we? Okay. Then if we look at how the Haines Index did for the Pagami fire, we see that the Haines Index actually dropped on the day for all three of the Haines Index variants, but the mid-Haines is the one that you're supposed to apply in northern Minnesota. And the Haines Index did not look to be a particularly good indicator for picking out the worst day on this fire. Okay, another example, here's the Double Trouble fire from New Jersey in 2002. This was a single day event that happened on June 2nd. And here we see again that hot, dry, and windy was very high on that day. It was high 2 days before, but there was no fire on the ground at this location on that day. So we don't necessarily know whether whether hot, dry, and windy would have been a good predictor or assessor of what sort of fire behavior was seen on that day. The other thing we see, looking at the Haines Index, we see that it was the low Haines was in fact high on that day. It got up to a 6. So there's some indication that maybe the Haines did have something to say about what was going on with the Double Trouble fire, but it's arguable. One could argue that hot, dry, and windy stood out better on the day of the fire. Now we're going to look at the Cedar Fire, our last example for right now. A 2003 fire that happened in Southern California. It was a Santa Ana driven situation. And here we see again that the hot, dry, and windy was the highest on the day when the biggest spread happened. And the Haines Index was basically high all the time and was bopping around and even went down a little bit for some of the variants on the day of the fire. So this idea, I mean, these sorts of checks lead us to believe, okay, the hot, dry, and windy, not the Haines Index, hot, dry, and windy does seem to be telling us something. But we have to question ourselves, do the numbers actually mean anything? And the answer is, well, they might mean something, but it clearly can depend on location. A 600 in one location might be quite common, whereas a 600 in another location might mean that that sort of thing has never happened before. So what we then decided to do was to compare daily values against climatological values. The CFSR is a reanalysis data set. We can look back at the 30 years from 81 to 2010 and compare those with the daily trace and see how the values stand out. So for each CFSR grid point in the United States and Alaska, continental United States and Alaska, we analyzed 30 years of CFSR data and created a running percentile analysis of HDW values that we can then shade and show where a given value falls within the percentile range of the CFSR climatology. So the idea is that if we're in the upper part of this graph where the darkest reds are, we're above the 95th percentile, that's fairly unusual conditions. Then as we move more and more towards the bottom through the colors and down towards white, we get to conditions that happen more and more frequently. And the individual dots on this graph are the individual values for each day of the year in the CFSR. So we're kind of showing the distribution and then how the climatology percentiles play out based on those values. And then what we can do, we can compute this climatology all over the world. I should have mentioned this is actually for Southern California near San Diego, just to pick a random example. Here we're looking at Green Bay, Wisconsin, because one of our developers is from Green Bay, so she insisted. Either way, we're looking at Green Bay, and what we get is a climatological distribution of what HDW looks like over the year. And this sort of analysis could be used or could help inform the starts of fire seasons and the relative severity of fire seasons based on meteorological information. There's some indications of sort of the bimodal distribution that we see in fire occurrence in some parts of the world. So some of this sort of analysis certainly bears additional investigation going forward. But what we're arguing right now, as far as a forecast product goes, is you can put the time series, and this is going back to Pagami, so we're looking at Pagami, but the time series of Pagami, we can see on the day when the big spread happened on Pagami, the value was well above the 95th percentile and getting up towards the highest values that appeared in the CFSR climatology. So it suggests that that day was very much a standout day based on the CFSR data for that location. And the other days before and after, there was one day that was above the 90th percentile, and there were a couple other days in the 75th and the 90th percentile. Those might also be sort of watch out days and where we can also look at what sort of fire behavior occurred. But clearly the big spread day was a very unusual day at the location of the Pagami Creek fire. So now we have a tool where we can go back and look at historical fires. So the next step is, okay, how do we make this useful for forecasting today? So we thought, okay, we have a CFSR climatology. We can compare this against the GFS ensemble. The CFSR starts with the GFS as its initial analysis, and then it assimilates data and other things to produce the reanalysis data set. So it's on the same grid. We have 21 members in the GFS ensemble, and we can compare them directly to the CFSR climatology in a forecast mode. And we can do this on any given day and for any given location. And this is the sort of thing that we see. Here's another analysis for Green Bay. And so what we're seeing here is we can look at the previous 10 days of the GFS analysis, so the GFS control analysis, and we can see what values of HDW were happening for the last 10 days, let's say. And then we get to the current day, day 0, and we see the first day forecast, and we see what sort of spread we have. Second day, the first day forecast, how much it goes up, then it goes down, and then we get more spread in the ensemble members as going forward. And we can do this sort of analysis for every point in the United States and Alaska, and every point in the United States and Alaska, and we can present that. So in order to do that, we have developed a website. And the website is just www.hdwindex.org. Anyone can connect to it. It's wide open, and anyone can look at it right now. And now I want to show you a couple of examples of what the website looks like. Let me find it. All right. So this is what you see when you first connect to the website. First off, we want to point out that this is an experimental research site. We're Forest Service researchers. We're not forecasters, so we're not arguing that this is a forecast product. Right now, we're still trying to investigate and learn more about how this thing works and trying to develop a tool that can be useful for forecasters to look at, with the ultimate goal of making this an operational tool if it has fidelity and it winds up being useful for people going forward. Top of the page, so right at the top, we say it's experimental research. Then we have a status update. The page is updated every morning. We run all of the analyses on here from the 0Z GEFS. We only do it once per day. So that means that for most parts of the continental United States, it's fairly early in the morning, and getting to Alaska, it's a little bit later in the morning, but it's once daily, relatively early in the morning or in the morning period when these forecasts become available. And the splash screen, if you will, or the opening page, it shows what the highest value is for any of the ensemble members for that particular day. So here we're looking at 25 July today, and we're seeing what parts of the country are showing high HDW values from the GFS. So we're seeing high values in Maine, high values in northern Maine, high values in southern Florida, in the southern parts of the Four Corners states, and also along coastal California. Now, from this page, there are two different ways of getting to the forecast product. One of them is you can just simply click on an area. So if we click on Southern California, it will bring up the same analysis that I was showing you before in the PowerPoint. There's a gap here at day -4. As we were developing this web page here locally, there was a day when the server was down, so we didn't download the data. So that just appears as a break right now. Going forward, that gap will rotate off or will slide off the screen, and then hopefully we'll have continuous data going forward. But this highlights we're a research group. So we're doing our best, and we'll do our best to keep this up to date, but occasionally there might be little gaps like this. But what I wanted to point out is that for this location in Southern California, you can see very high values above the 95th percentile in day 0, and then in day 1 and 2, still very high values. All of the ensemble members are above the 95th percentile, and then going forward, we have values between the 75th and 95th percentile for the days going that. You can see that there's not a particularly large spread in the forecast for this particular location. Now we can also go back and click on other locations. So let's look at northern Maine now. So if we look at northern Maine, we see day 0, we have high values as indicated by the map. And then next day, it drops way, way, way down. And the day after that, it goes back up again above 75th and 90. And then later on, we get much more spread in the various ensemble members. So it gives you some idea of the confidence of the GFS and also how the values are varying compared to the background climatology for a given location. All right, so that's one way of looking at the forecast data. The other one, hello. Sorry, my screen just tried to go to sleep for reasons that I can't quite understand, but hopefully I didn't lose you all. But anyway, the other way to look at it is you can come up here and you can actually enter in a lat long. So if you're out on a fire at a certain location and you don't want to count on being able to click on it, you can go down and enter in a latitude, longitude. So we can say 43, and we can go down to minus 108, and hope I didn't hit something over the ocean. Let's see. Okay, so and you can get a forecast or an analysis of that particular day for this forecast tool. All right, and then the other thing that you can do up here in this pull down, we have the analysis plus the forecast. You can also look at the climatology for that location. And you bring up the climatology, you see I hit pretty much the middle of Wyoming. So I guess that's pretty good. And you can see what the HDW climatology looks like for that location. So you can do this for any point on the map. Click on it or enter in the lat long. And also down the left-hand side over here, there are various other products and tools or pieces of the HDW webpage that we put together. Just recently, within the past 48 hours, we have put together a similar page for Alaska, and the Alaska map is not yet clickable, but it should be soon. But if you entered in a lat long for Alaska, you could also pull up a similar analysis for anywhere you wanted in Alaska. And you can see what it looks like over there. Okay. And then going back to the main page, we have an about page that basically has the same information that was part of this presentation that I went through. So looking at the YVPD, also has links to the 2 publications that we have for hot, dry, and windy that have recently come out in the Atmosphere, Fire, and Weather Special Edition, special issue. So you can click on those and find those as well. How the climatology was produced, about the GEFS, caveats and known issues that we'll talk about a little more in a moment. But basically, if you wanted to see a much more detailed account of how the index is calculated and how this tool was put together, you can connect to those 2 papers. We also have a number of case studies that we're putting on the page, basically analyses similar to the one that I just showed you for a variety of fires. And we're putting these together for a number of different fires, and we're always looking for more fires to put on here. So if there's a fire that you either were working on in the past or that you're curious how HDW did, let us know. And if it's in our CFSR data set, we can easily bring it up and produce an analysis just like that. We also have a mobile site that's basically all of the same information, but it's organized so that it won't like scroll off your screen or get all out of whack if you look at it on a mobile device. So we have that as well. And then we have contact information here at the bottom. So with that, that's the overview of what's on the website and sort of the background information. Now, there's a few caveats that we want to offer. Some of the ways that we already know that HDW can fail. We know that it can fail due to spatial and temporal variability of weather phenomenon. Right now, this web page, it only looks at data at 12Z, 1800, and 0Z for the continental United States, and it looks at 18.0 and 0.6 for Alaska. So anything that happens on a shorter time scale than that has the potential to not be well captured by the GEFS. It also depends on model accuracy. If the GFS or the ensemble doesn't pick it up, then there's no way for HDW to know that it's there. And also model resolvable phenomena. This is still a very coarse product at this point, half degree grid spacing. So we're not going to pick up fine scale things like thunderstorms and valley flows and topographic features, and even land sea boundaries are going to be a little bit mushy in this model. So we have to focus on the idea that we're looking at large scale weather phenomenon and sort of mesoscale towards synoptic scale variability, and that's what we're trying to assess with the index at this point. So with that, I am now going to hand it over to Brian and have Brian talk to us for a little bit about his experiences with his thoughts on indices and the daily use of HDW. Still there?
Yep, I'm here. Can everyone hear me or anyone hear me?
I can hear you.
Okay, I'll assume that means everyone can. All right, so just a few things I wanted to add on to what Jay presented. First, and I don't know if Jay realized this, but for the climatology on the website, you have to enter a lat and long. You can't click on the map. Clicking on the map always goes to the ensemble forecast. So my other comments. First, a thought on indices. And many of you have heard me say this before, but I will say it again to them. And anyone who hasn't heard me say it, you're going to hear it, but you'll hear it many times from me if we start talking. Indices are indicators. They are not meant as the final point in an analysis. They are to tell you when you need to look more deeply at something. Misuse of an index, relying on it alone or using it for something other than it was intended, puts all the ball in your court. That's when you have no background on what your application of it is going to lead to, or whether it was really scientifically sound for that. The way I use hot, dry, windy in the Northwest, and I've been, let me preface this a little bit. I'm in the Seattle Fire Lab. We've been working on hot, dry, windy for several years, so I've actually been looking at it on a daily basis throughout the fire season for the last 5 years. And actually going back to its roots, I played with an earlier version of it, looking at the Black Saturday fires in Australia from 2009 using their Met forecasts. And that was one of the things that led us to think that maybe it would work as a daily product. But I look at it in the Northwest on a daily basis during fire season. I look at three different formats of it. I look at a WRF output from the University of Washington. I look at NAM output, and I look at the GEFS output that you guys just saw on the website. I look at it for a quick sense of where the hot spots are. So when I see that map Jay showed that has a dark spot in Washington right now over the east side of the Cascades, and I'm going to pull it up to make sure I reference the right area. Yeah, so just east of the Cascades or down in the Central Oregon Cascades, that's where I would go and zoom in, especially if I knew we had fires there. So from that's sort of taking a GAC type perspective. I'm looking at an area, looking for the hot spots or the hot, dry, windy spots, and zooming in from there to see what the overall conditions are that might lead to the index getting that high. If I know of a point I'm interested in, looking at it as more of an IMET type approach, I will immediately go and I'll look at that location as the time series from the GEFS. One of the beauties of the website, the way Alan and Jay built it, is if you look at a time series for a point and you bookmark that page, once you've got the time series, that bookmark will always go to the most recent version of the hot, dry, windy GEFS forecast. So an IMET can tag it, and then every day you don't have to go back and find your lat long again. That bookmark can pull it up each time. And so I might pull up one of those time series like Jay was looking at and see how's it look going outward. And so, for example, this morning on the Northwest fire call, I looked at it, and a lot of the spikes that I saw where it was getting up towards 95th percentile were all coming sort of Sunday-ish. And at that point, the GEFS variability was really scattered. So I was like, my assessment would be, okay, that's the day to watch for, but keep watching because there's a lot of uncertainty in that forecast. We want to see how it plays out as we get closer. It's an indicator. I go from that to looking at synoptic maps. I might go zoom in on the UW's 4-kilometer grid, so I get a higher resolution forecast of what the winds or the humidity might be doing. It was also showing for the last couple days and the next couple days that vapor pressure deficit is going to stay very high overnight on the east side of the Cascades, and that was echoed on the call. I didn't have to say anything on the call. I usually just lurk because everyone was talking about poor humidity recoveries. So you can dig in if you want. If you already know the details, then the hot, dry, windy page is really not going to tell you a lot more. It's for that first check. If you know the Zen proverb about the finger pointing at the moon, it's the finger. If you've already looked at the moon, the finger is kind of superfluous. It's probably more productive for me to stop there and let Jay and I take questions than it is for me to ramble on. So I will stop there.
Okay. Alrighty. Okay, now I got to do a couple more quick slides, Larry, and then I'll be finished up.
Sure, absolutely.
Alrighty. All right, so after the Brian Potter interlude, All right, so we do have a few planned next steps for HDW, well, a number of planned next steps, and I'm not going to go through all of them because we would be here all day, because we're researchers. We can think of a million things to do with this stuff if we set our minds to it. But some of the things near the top of the list is we do want to establish an ability to archive HDW data so that we can more readily look at past cases and even save HDW values from the website and from other locations for future case studies. As I alluded to when going through the web page, we are always interested and continue to be interested in more case studies to add to the website using either CFSR data or whatever data anyone wants us to look at. We could conceivably look at it and put it up there for people to compare. We're open to that as long as if someone wants to bring their own data and say, hey, I have this, compare that to CFSR, I want to see what the differences are, let us know. We're happy to talk about how best to do that as well. There are a number of different research projects that are going on within the four of us and with various students and other researchers that we're working with, looking at HDW with different forecast models at different time scales and for different locations all around the world. So all of this is very much an ongoing research effort and experimental effort, and we're always happy to talk to people about ideas about either improving, modifying, or assessing, validating the index. And basically anyone that wants to talk to us, we hopefully are pretty easy to find. So that leads to, how can you help? First off, we want any and all feedback, good and bad. If you think it's telling you something that you weren't getting from other locations, and you can use it either as this is helping me prepare a forecast, or even as a communication tool. If it's straightforward to say, hey, today's a 65 HDW day, to when you're communicating with fire people, as opposed to, well, tomorrow could be a 93. So watch out for tomorrow, but today, at least based on this index, it might not be that bad a day. That's useful information, and we'd like to know if that's a way that you feel that you can use this product, or if you feel like that's not a good idea. How do you use HDW, or how could you conceive of using it? We're open to any and all ideas at this point, and want to help investigate them and nail them down. As we said before, we're always looking for more case studies. We want both successes and failures. If there are big days that happened that are not captured by the type of weather we're looking at, we want to figure out what, if anything, we can do with HDW to capture those sorts of days. And then the other thing, we're always on the lookout for high resolution, particularly high temporal resolution, fire spread, fire evolution data. Like if we have hourly spread data over the course of a few days, and some of those hours are really bad and other ones were not so bad, and we think that weather might have been a factor, we should talk, and we really want to try to look into those sorts of cases. So with that, I will close off and say thank you to everyone, and I'll put my little pain level right now. Hopefully we're back towards zero, where we're just kind of in a zone and trying to think about this rationally and figure out the best way to go forward. And also here at the end are the references I referred to the recent papers, Schrock et al. And McDonald et al. That describe the sort of background information that led into this presentation and the material on the web page. So with that, I will bounce this back to Larry, and we'll take any and all questions that come our way.
Great. Thank you, Jay, and thank you, Brian. We really appreciate this outstanding presentation on HDW. I think it's pretty exciting work you guys are doing. I'm going to start off the questions. I got two questions for you. One, so the HDW shows a percentile. So has there been any work or any thought on what does that translate into? So, if I'm seeing 95 or higher, and I'm expecting, a really active, busy day, but what does 93% mean, or what does 90% mean? Is it something where you could say at X percent, or at X percentile, you could see Y percent of the time this fire behavior or this kind of action?
Yeah, well, thus far, the percentile ranges that we're presenting on the web page are as much for visual purposes as for any direct connection to physics of the fire-atmosphere interactions. We found that if we put a higher percentile threshold, like we tried to go up to 99%, we got some really jagged-looking lines that felt like it made it harder to interpret rather than easier. So that's why we chose 95%. The idea being, I mean, right now, the way that the page is put together, it shows how much of an outlier day this is compared to climate. It doesn't necessarily say anything direct about what sort of fire behavior you should expect based on that percentage.
Jay, are you still there?
This is Brian's still here, so I'll take over because we share a brain.
Okay.
Okay. Yeah, he was walking right up to the comment I was going to make, which was, remember, this is an index, it's an indicator, and it's weather only. So your question started to address concerns more along the lines of how it's going to interact with the fuels and specific fire behavior. We don't have it locked into anything like that at this point. There are so many ways in which hot or dry or windy influence a fire that, as it stands, it's sort of an aggregate indicator of potential atmospheric influence on a fire.
Okay.
Does that make sense? When I look at it on a daily basis, again, I'm looking at a quick snapshot. If it's spiking above 95, I'm immediately interested in that location or that day. If it's in the upper 90s and it's going up to that, or I mean, if it's in the 90 to 95 and that means it's jumping up from what it has been the last week, then I note it. But, you know, you could have been in the 95th plus for 5 or 6 days and it drops down to 90th, in which case a 90 is less worrisome to me. A 90th percentile is less worrisome to me than it would have been if we'd been sitting in the 50s all the last week.
Mm-hmm. Okay.
Back now, Larry. Sorry about that.
No problem. Yeah,
right,
Brian, just finish your thought.
Last long enough.
Okay, thank you. And my second question is, do you have instances where HDW pointed out some low times or times where the Haines was showing as high, or as a meteorologist, you inherently kind of looked at a situation and thought, boy, this could be a busy day, and it turned out that HDW was saying, no, maybe not, and it did turn out that it wasn't a busy day? And I say busy day in the, you know, the just the general sense, but.
I think I'll pass that one to Brian, who's looked at it more on a day-to-day basis than I have.
Right. Yeah, so you're asking about confirmed negatives that go counter to the rest of the data.
Correct. Like I said, you know, you're kind of looking at the Haines. The Haines is indicating high, or just inherently you're out there going, boy, you know, it's dry. You know, I don't know. It could be a normal to busy day, and it turns out nothing. It was no big deal.
Right. I can't say that I've tracked any specific days like that, but I can tell you exactly the circumstances where I think it would happen. An inversion or a smoke layer that's blocking off the Haines layer. Since you went to Haines specifically, and I'll not extemporize on that, but
that's a perfect example, though. You know, with an inversion, you know, you can have everything seeming to set up, but boy, you get that inversion and just it caps it off. And
yeah, that's usually where, if you were looking at the Haines, you would think that that's the situation where the Haines is not going to work at all. But that's I don't have any specific days I've spotted that, and the reason for that would be that the GEFS certainly doesn't include that inversion or that smoke layer any more than the other whatever model gave you the Haines. If you were running off of surface-based, essentially belt weather kit slung wind speed times the vapor pressure deficit instead of the 500 meter layer we built into this, then maybe you would chronicle that, but normally you wouldn't. If you were concerned about another scenario where I could see hot, dry, windy failing, it wasn't really a fail, it was a confirmed negative. Another situation where I could see it giving you a low risk day and the low risk bearing out, while other things said a problem would come up, would be if you were expecting a big wind change to be your problem issue, but the wind change didn't affect the location of the fire particularly well. In which case, I mean, hot, dry, windy does not include any directional information. It's actually possible to present it as an arrow, just put the wind direction on top of it. We've not looked at that yet, but that second scenario I'm hesitant to call a win because it relies on a busted forecast in the first place.
Right. Okay.
So
are you guys looking for examples where folks have been out on a fire and seen a strong inversion, or a capped off or smoke inversion, smoked in, and examples where they thought things might get active and they didn't?
Yeah, that'd be great.
I'm sorry, I talked over you. Go ahead.
I think we talked over each other. I think we all agree that would be interesting to look at.
Okay.
We're scientists. All data is always good.
Excellent. Well, there you go, meteorologists out there. If you've both the really big active days and maybe the days that thought you was going to get active and you just got smoked out, whether it was your fire smoking it out or a fire upwind that smoked you out, and let these guys know so that they can take a look at it. Let's go over to our attendees. I'm going to start out with Julie Rutherford. Julie, I'm going to unmute you here, and if you can go ahead and ask your question. Julie, are you with us?
Yeah, I'm here.
Okay.
So what I was curious with, if you've got, is there a way right now that on the fly you could do, IMET could do adjustments for local scale effects? Say you're on a fire with something the model's not going to pick up, but you want to adjust it based on what you're expecting your local winds conditions to be. Is that something you do, or is there a way we could input, like if we launch a balloon sounding on the fire, is there a way we could calculate the hot, dry, and windy index manually off of that?
There is not currently, but that's something we can add to our data stream, and we might have to figure out how to control that a little bit. In that, if we have input values that you have on a fire and calculate hot, dry, and windy, and calculate the index and compare it to others, it's just we can't leave that wide open, I wouldn't say. We might have to talk to individual users about how to test that properly, but that's something that we could work towards implementing. It could be a bit of a programming issue, but we can get there. So thanks,
yeah,
Julia.
I think that'd be super useful. Or if you had a way to, like a way you could game it out, not that it would end up on the site in the end, but if you could say, okay, hey, if it was 10 miles an hour windier than what we forecasted, what would that mean to the index? Just a way you could play with it to see like sensitivity analysis for where you're at on a kind of in a real-time basis would be a super useful tool.
Cool. Yeah, that's interesting. Yeah, we will certainly write that down and consider how best to do that.
Julia? So this is Brian. I'll throw out a comment. The scale thing is really, really important. Just as an illustration, hot, dry, windy for the Dalles, Oregon right now is showing that for the next 3 or 4 days, it's going to be in the 100 to 200 range from GEFS. But if I go to the UW's WRF output, it's putting the surface-based hot, dry, windy in the 300 to 350 range, and after sunset, it seems to be remaining in the mixed layer, or in the lower 500 meters, remaining as high as 350 to 400. So adjusting it to local conditions, what as an IMET on an incident or something, I'm thinking, I don't know if a tool is going to do that for you, as well as experience at that location, watching what hot, dry, windy says on the GEFS forecast and what you get while you're there, and figuring out how I mean, if you see that, if you decided to sling weather and you found that at the base camp or wherever it was consistently 50 to 80 points higher than what GEFS says, then apply that to your own interpretation. Or if you noticed wind directional dependencies in that, but that requires the IMET to build up their own on-site information, and again, hammering on the index point. At that point, I think you'd be better off putting your attention into the rest of the forecast and not focusing on hot, dry, windy's overall general picture.
Okay. Julie, did that answer all your questions?
It did. Thank you.
Excellent. Thank you. Our next question is from Brian Blaylock. Brian, I'm going to go ahead and unmute you right now. Brian, you have the floor. Brian, are you there? So Brian had asked, to get better spatial and temporal resolution, have you considered using the HRRR?
Yeah, this is Alan Strock here. We have considered looking at a bunch of different models, and so yes, that's actually something that we have a student at Michigan State working on right now. One of the big questions, and this ties into what Julia had asked, the comparison to the Climo is going to be very dependent on the input data. So making a trace of HDW from something like the is very easy, but how it compares or...
Alan, you're breaking up. Alan or Brian, are you guys there?
Brian's here.
Hey, Brian. And Jay, are you still with us?
I think Alan and Jay were on the same phone.
Aha.
I'm
Must
gonna,
be budget cuts.
otherwise I don't think Alan could have responded to that.
Right.
I'm going to toss out that one of the points he was making was that we only have the climatology aspect for the GEFS forecasts. And so while we could run with finer scale models or something like that, we don't have the climatology to give you percentiles.
Okay.
Hello, we're back again. Sorry about that.
Oh, yeah, not a problem.
Okay. Did you want Alan to continue with what he was saying, or we move on?
Yeah, go ahead. Sure.
Okay,
Okay, so not sure where it cut out. So basically the idea is any different data set is going to have its own inherent kind of maximum and minimum values. You would expect, for example, the HER at its 3 or 5 kilometer resolution, depending on which version, could better pick up something like an outflow boundary, for example. But that's going to introduce different, say, percentiles if we were to build a climatology off of that. In order to validate HDW and to build something that we knew could work globally, we stuck with CFSR because we had 30 years of continuous record. So you could do the HER, you could do a trace of it. My biggest concern with that or with any of these other models or changes would be what will happen or will the comparison to the climatology background be valid? If you're just looking for the trend, though, in, say, what the HER does from one day to the next, and that spikes and GEFS spikes and other things, I think there is usefulness for that. But it's something we are looking at. We have a student here at Michigan State looking at it, and we will be continuing to work on that and share that information as we go along.
Great, thank you. Appreciate that. Let's see, let's go to Chris, and sorry about mangling the name, Matorokia. Chris, I'm going to go ahead and unmute you here. You should have the floor. Chris, are you with us?
Yes, I am. Don't worry about the last name. Happens all the time.
Okay.
Thank you for giving me an opportunity here. So this is really a great product, and I want to thank all the people that put work into it. Currently, I am embedded at the California State Office of Emergency Services. I'm the liaison for the National Weather Service. One thing that we're really trying to do in California is create a tiered fire weather index, or like a fire risk. So, you know, we can say this is a level 1, a level 2, a level 3, a level 4 day as far as risk of fire spread. What they really want to see here at the state office is like a map of California and a GIS format that kind of highlights which days would be most probable or most likely for a high risk of rapid fire spread. Because that's something that happened with the Thomas Fire, which was the largest fire in California history from December 4th of last year, and would really love to see a reanalysis on that. So I think this has potential for us to use for the entire state of California. And another question I just had too, I know I'm throwing a lot at you here. We would really love to see this. I don't know if it's possible that this can be produced in GIS shapefile format just for maybe the state of California, because that's what Cal OES wants here. And also, does it take into account anomalous wind directions? Because during the Thomas Fire, you know, we have something called sundowner winds here in California. So anomalous wind direction really plays a huge role into this, in addition to anomalous wind speeds. So I'll just end my diatribe there and see what you have to say. Thank you.
All right. Well, I'll start out here. First off, as it's currently formulated, hot, dry, and windy does not have any wind direction information certainly in what's on the web page. We have had discussions in the past about ways of trying to incorporate wind direction and wind shifts and that sort of thing into it, and it's complicated, as we all know. And how best to do that, we kind of have to sacrifice simple in order to get at some of those answers. And once you sacrifice simple, it becomes harder to track down why the index may or may not work in a given situation. But that doesn't mean we shouldn't look into it. It just means it could be more complicated, and it'll be more of an adventure going forward, let's say, trying to figure out what it all means. As for the other questions about applying hot, dry, and windy or having it in GFS format, applying it to California and to historical sort of situations like this, I, for one, am very willing to talk. We're all willing to talk about how best to do that and how to serve the needs of individual users and customers out there. And whether we're the best ones to do it, whether we should consult with someone else for how to set it up at a given office or a given location, or whether this should go through the Weather Service and wind up being a Weather Service product that meets that particular need. I think all of these options are potentially on the table, and all of them are worth discussing. So I would ask, and I'm terrible with names even on the very short term, but I believe it was, I'm not sure what the name of the individual was who just asked the question, but I would totally
Chris.
Encourage you to send me. Okay, so drop me or us an email with your name, and we can get on the phone at some point and talk about what should be the right next steps to try to make this product something that would be most useful for you. And
one more quick addition from here. The data format that we're using is NetCDF, and there's ways to read that directly into GIS. So theoretically, getting you a data file that you could play with would not be terribly difficult. It may not be the most efficient, but we can figure something out there. The other thing is I was watching the Thomas fire when it happened. I didn't archive the images because I wasn't thinking about it, but it did pick it up. So if the GEFS is picking up some of the sundowner flows because of the direction of the flow and some of the processes that go with it, it did very much light up at that point. And that's one of the cases we have on our list to add to the website. Actually, a few of them from that December in California are very, very interesting. So we're going to put a few of those up on the website here in the next 2 days. If you have any specific detail, that would be great.
This is Brian. I'll just throw out that Airfire has a lot of experience converting weather model output into KMZ files and things like that. We do it with the Blue Sky Smoke Modeling Framework all the time. So one way or another, we can do that. We collectively, all of us on this call or whatever. The other thing about the Thomas and the sundowners is the hot, dry, windy lit up, if nothing else, because of the synoptic scale, the Santa Ana winds. The sundowners and the fine scale of those is well below what the GFS would have directly forecast. However, there could be gradients that it's catching that would allow fine tuning like that. But I'll go back to my index warning. At the level we're producing this, at a 0.5 degree and at a once-a-day snapshot, you are far better off digging into your local weather model to decide whether you've got to worry about those short-term, small-scale features. You're starting to use the finger instead of the moon.
Yeah, I was just looking for something that's more of like a broad brush. I mean, I understand it's not going to be able to get to that fine scale, but just for planning purposes here at the state office, just if they can have, when an area lights up, they know, okay, well, we have to pay more attention to this. So let's look more in depth at this day to see, exactly what the details are. It's they're looking at it here just basically like a situational awareness tool. That will raise their attention. So yeah, the finer details, I mean, our local weather forecast offices in California do a really great job with identifying, when sundowners are likely, and we're in one of those stages right now. But to be able to just present this on a day-to-day California map basis in a GIS format would really be great for the folks here, and I think it would really be great for everybody that's involved in this project as far as exposure and proof of concept for this gaining traction and spreading. So I'll send you my email, and we can talk online, and maybe if I'm here until the end of September, so one of my goals here is to create prototypes of new products that'll help the state office here plan and allocate resources a little bit better. And I would love to work with you folks to have something maybe to present to some of the upper management here. I think they would love to see it, and they would be really happy with it, and we can expand from there.
Sounds good.
Great.
Thank you.
Thank you, Chris. Our next question is from Joel Curtis. Joel, I'm going to unmute you. You should have the floor now. Joel?
Well, thank you for this. I think it's a really, really promising index, and I promise that I'm only going to use it as an index and not, the main deal. But my question was, have you explored looking at the trends in HDW as sort of a preparation for fire danger? Have you examined these trends or periods where you've stayed in a high percentile and then that increased the fire danger, and sure enough you got those results that the 1,000-hour fuels had really dried out, and boy, this place is ready to go? Have you guys looked at that at all?
Yes, we have started looking at that and intend to continue looking at that through a number of different students that are looking at this data right now for various projects, and looking at like lag correlations between the big fire day and how the index varied on the days beforehand. And so that's very much a part of our thinking, and very much a part of our plans going forward, is to try to see if we can identify other sort of watch out conditions other than this day, quote unquote, instantaneously is big, therefore that's the day you should watch out for. If you see a trend or see a sequence of days that are in a certain range, that could also mean something else. And we're trying to tease out as much of that as we can.
Thank you.
I've got a preliminary result on a study that I'm doing that suggests, I'm going to use the hedge words here, that the sum of the previous 10 days, hot, dry, windy, may influence the size of a fire on the first and second days. So that sort of points to the idea that prolonged high values can lead to greater fire growth, but there could be more to it. The flip side of that I'll mention is when I looked at the Northwestern fires, PNW, Washington, Oregon, for 2015, and I'm seeing this a little bit this year, the fuels here are so infernally dry right now that the dry part of hot, dry, windy seems to be almost irrelevant. You can't dry anything anymore, and it's not getting any wetter. So it's really just the wind that matters when you get to a certain point. So this goes back to the whole thing. You got to know the whole picture to start interpreting what it might mean. If it's low or if it's high, you should still be looking maybe, but why it's high may be more important.
In some situations.
Yes.
Thank you. That was excellent.
Okay, thanks, Joel. We're going to take our last question here, and this is from Matt Jeglum. Matt, I'm going to unmute you. You should have the floor. Matt, are you with us?
Yeah, can you hear me?
I can.
Okay. My question was, so when Haynes did his work back in the 80s, he used, I think, like 75 fires or something to calibrate the Haynes index. And a couple of questions have touched on this, but I was just curious if, with the huge archive of daily fire growth data that we have nowadays, have you guys investigated calibrating this using actual like daily fire growth over, either fire weather zones or WFOs or regions? Have you looked at it, and did you reject it, or is it something that's still an open question?
I would say we've looked at it and are continuing to look at it. It's certainly not rejected, And there are connections. I mean, Brian in particular has a data set that we've been comparing numbers with, and that was what led to some of our initial. I mean, we did actually look at a hot, dry, windy style index with relative humidity, with other variables in there to see, does 500 meters make sense? Does just looking at surface values make sense? What gives us the best sort of relationship to sort of the daily fire growth data? And the numbers, the formulation that we're looking at right now is the one that gave us the best connection or the best correlations, if you will, for some of those initial assessments. But going forward, we fully intend to, our intent is to continue to compare hot, dry, and windy values with different meteorological data sets to this growth data. The complexity comes in that every data set has its own idiosyncrasies. The growth data is full of idiosyncrasies as well. And so some of the correlations are perhaps a little bit uninspiring, but at the same time, we can learn what we can learn from them and try to refine the index either down to regionally or to different temporal and spatial scales or different sorts of applications based on the data we have. So I don't think anything's been rejected at this point, certainly not. But what exactly we're going to try to assert from both the scientific standpoint and from a how could one use these sorts of numbers is our questions we're investigating going forward.
Okay, cool, thanks.
Thank you, Matt. Jay, Brian, and Alan, thank you very much for your presentation today. We certainly appreciate it. That concludes today's episode of Fire on the Fives. You can catch this episode or any Fire on the Fives episode on YouTube by searching for NWS Fire Fives. This webinar is a presentation of the Fire Weather Program of the